All right. Let's see if this is working here. Yeah. I see you. Hold on. Let me see if I can hear you. Can you hear me? All right. There we go. I can hear you now. That rig you put together for your phone is amazing.
Yeah. It was like all the stuff I have from painting my basement, just sitting down here.
Perfect.
Yeah.
Well, thanks for doing this with me. For those who are tuning in, hello. This is my first Instagram live session, and this is James Davenport. James, I'm going to let you tell people who you are, and we'll go from there.
Okay. My name's James Davenport. I am an astronomer in Seattle. So I have a PhD in astronomy from the University of Washington. I've studied at a few universities around the country, but I am back at University of Washington now, where I got my PhD. And yeah, I don't know. I mean, I'm just a guy, you know.
Well, no, you're more than a guy, because it's first of all, it's been a long process. You've gone to, you've got your master's, you're a PhD, right? I mean, all these things that have been just a growing process to where you are now.
Yeah, that's right. So just, yeah, okay, to give a little more detail. So I did 5 years in college, just because I took my time, and was really bad at like math. Had to redo some math classes. And then I did a master's for 2 years, which is a little unusual in astronomy in the US. Usually you just go straight to PhD, but those math class, that GPA wasn't so high. And so I did a standalone master's to kind of figure out if I was serious about this life as a scientist thing. And then I went and did 6 years for a PhD. And I graduated. I got that about 3 or 4 years ago. So I've had my PhD now for almost 4 years.
Awesome. I mean, I guess, how important is the math? I mean, is it something that's super crucial to what you do?
Yeah, I mean, yeah, it's important. Like,
Yeah.
it's definitely important, right? Like, I have a lot of fond memories. I had a really lucky experience with a math teacher in high school who, like, it really clicked with, right? And one of the themes you hear when you talk to scientists or academics or historians or whatever is like, I had this one teacher and they like blew my mind, and and like that made the difference, right?
Yep.
And like the role of mentors and inspiration is like super critical. And for me, I had a math teacher. I was lucky enough to have him. I grew up in a small town, like 400 people at my high school. So
Where you up?
I went to a high school called Natchez Valley High School. Go Rangers. Yeah, so it's about 3 hours east of Seattle, kind of in the foothills of Mount Rainier. And it's like a rural agricultural community, and like 2 of us from that high school class went to University of Washington.
Right.
So it was a small town. I was so lucky to have one great math teacher who was able to teach calculus and say the things in a way that like stuck in my brain. You know what I mean?
Right.
Like that was the key.
Absolutely.
There was no physics, there was no astronomy, there was like very basic science in my high school. I was just like a nerd who went to space camp and like watched Star Trek, but I got enough educational footing that I was able to actually get into university. So I was very lucky in that way.
Sure. And so now you're on a path where you're doing all this research, and specifically you've been working a lot with Kepler, right? So when did that start? When did you start digging into Kepler?
Yeah, so Kepler mission launched in 2009, which is the same year that I started. Oh, is that true? Same year I started my PhD? Yeah, it is.
Yeah.
Yeah, so it launched right after I started my PhD. And like in the first like 6 months of my PhD, a friend of mine came back to UW and gave a seminar saying like, check out the hot new data off this new telescope, which I had barely heard of. And I was doing nothing related to it. I was working on old data that had come off a telescope maybe a decade later or earlier. And, I was working through other stuff. I was a young student. And she came back, this is Lucianne Walkowicz. She came back and gave an amazing talk, just saying like, look, Kepler, it lives, it's in space, and it's doing cool stuff. And it was just like a show and tell. And I was just like,
sign me up.
Oh my God. And I was like, I got to be involved in that. I got to join that on some level. And so I kind of like dipped my toe in. I still was working for my PhD. Hey, greetings from Brazil. What's up? I was like checking out the messages as they come by. And so like in the middle of my PhD, I still was sort of progressing on this other project. That's where me and my advisor thought we were going. And then I just found myself spending all my time working on Kepler. Like it was like the side thing that just consumed me. And I was like, nobody cares about this other stuff I'm doing. I got to work on Kepler. It's just so hot. And it was blowing up in the news. And so halfway through my PhD, I dropped my thesis project entirely because I realized that it wasn't hot. It wasn't happening. I wasn't excited about it, and no one else was either. And so I said, I got to go for it. I have to just follow my nose, because being an astronomer, being a scientist, an academic, it's a life full of like failures and challenges. It's a hard gig. You're always hustling. You're always.
You've been working something for years and never see results from it, right? I mean, it's...
Yeah, that's right. That's right. Yes, you can't make nature do what you want. You can't make the math do what you want. Computers are fast, but not infinitely fast. You know, like there's just challenges all the time. It's if you're good at it, it's hard.
Right. Even if you're good at it. If you're not, then good luck.
Yeah. If it's not hard, you're probably not doing something right.
Right.
So, so I was like, I got to go where my heart is. I have to go and work with Kepler data because I'm way more stoked about this. Knowing that a ton of other people were also excited about it. And so it'd be okay to be second at something as long as I cared about what I was doing is what I decided.
Sure. I mean, you don't have to reinvent the wheel. It's just as long as you're putting 100% to it, then you might come across something that people haven't yet. You know,
there's this attitude in science. It's not just in science, but like there's a very protective attitude about what you're working on in your data, and people want to be. Sometimes people want to be very secretive.
Sure.
And one thing that the Kepler mission really showed the science community, the astronomy community, is there is major value to being very like open and communicative.
Well, I was looking at your CV, and you were kind of it seems like when you made findings, you would share it to almost like an online forum of other astronomers, and people would chime in, ask questions. I couldn't see the questions or the comments, but that's what it seemed like, that it was a collaborative effort. But how do you also, which is great, and you can elaborate on that, but also how do you make sure that you're not wasting time by looking into something that 30 other people are looking into at the same time as you?
I mean, like that's a risk, right? Like, and especially when Kepler first launched, there was a major risk that so Kepler's primary mission, and like the thing that got everybody excited, was looking for planets around other stars, so-called extrasolar planets. That's not specifically what I spent my PhD doing, mostly because I was 3 years late to the game by the time I really dug into the Kepler data. But the people who were there on the front lines, trying to discover the very first planets, they were being very protective at first because it was so precious. It was like, these 4 planets, we got to like protect them and guard them. Don't tell anybody about them until we publish them, because it was a limited, right? It was a limited asset.
Yeah, and it was huge news. I mean, every time they discovered an Earth-like planet or anything along that, it was always huge news.
Totally, exactly. And so, and that's the same way it was like 10, 20 years ago with supernova. There was this huge project to do supernova 20 years ago, and like people were like, oh, I got my 12 supernova or whatever, and it's like a super big deal. And now we find 12 supernova at night, and it's like, and the same with planets, like almost 10 years ago when Kepler launched, people were super protective of those first planets. I wasn't early enough to that game to really care about that. And so by the time I jumped on the Kepler bandwagon, it was like, what do I have to hide? I am way better served by making what I'm doing open and available. And so I've learned so much from sharing. I mean, I have written entire research papers based on exchanges I've had on Twitter.
Right.
And like just tweeting out like graphs and ideas, and then just exchanging those with other scientists and even members of the public has been like a mind-opening experience for me.
Yeah. So social media is essentially changing the way that even research scientists work, which is funny because you think of it like more of like an old school kind of thing, but now I guess it's becoming more of our generation where there's different ways of doing it.
Yeah, that's right. That's totally right. Cool. And like, you can't like force young students to have like Twitter profiles or whatever, but like it's definitely like anybody who's out there who's watching this or who is talking to me in the future, and like, how can I get my work out there and get my brand as a scientist? Because that's really what you're doing as like a graduate student working on your PhD. You're working on your science brand. You can't study everything. You got to be known for something.
Right. You pretty much became an expert in one thing, or you tried to, I guess.
Yeah, that's right. Or like a handful of things. And And the truth is, I study lots of things. I mean,
Right.
I'm interested in a whole bucket of of science things, but
Cool.
people know me about one or two. And Kepler for now is like the thing that I'm working on.
So tell me, what have you been looking at? What's the data you've been studying? I know, see, this is what's funny. People talk about the exoplanets. You see articles, and you just see this drawing, like what I posted yesterday. This drawing or artist rendering of a planet, and it looks amazing, and it's surrounded by beautiful star, and it's just one of those things where that's not what you're looking at. It's kind of fantasy in that sense, but I guess from what you report to everyone else, that's how they know what to draw up. But that's not what you're looking at.
No, that's right. The reality of being a scientist is almost always like way more boring than you expect, right? Like, it's much less like Indiana Jones and much like just, I'm sitting in my basement right now. It's more like nerdy dude in his basement on his computer. So, so really when we talk about Kepler data, we're looking at, it looks more like the stock market, to be honest with you. Like you imagine, like when you think about the stock market, like these sort of time resolved wiggles, with some sort of a time series analysis of numbers, right? And if you can use those numbers that you've seen to predict the future, then you will have unlimited money from the stock market because you will have solved, the greatest challenge of human history, of making free money. But in the case of science, stars are much better behaved typically, and planets are much better behaved than the stock market. And so we can actually use, a year of studying or 10 years of studying a star to predict what it's going to look like tomorrow. And so that's really what my work usually looks like. When we're looking for a planet around another star with Kepler, or with its successor mission now, TESS, what we're really looking for is like a change in the brightness, like a very small dip in the brightness that lasts an hour. If in the case of the Earth, the dip would last an hour or two every year. Once a year, the Earth goes around the sun. We know 365 days. So you get like an hour, a little boop, a little blip, tiny little change in the brightness, and you're looking for a little wiggle in that little stock ticker.
How hard is it to find that?
It's amazingly hard. It's like you need the precision of, it's like 100 parts per million or something, precision in the ability to measure the brightness. And that's like ridiculous, right? Yeah. They make these, I don't know, I should be a better astronomer and know these offhand, but there's some analogy of like, this is like a bumblebee flying in front of a stadium light or something, like it's an incredibly small change in the brightness that your eye would never pick up.
Sure.
In fact, the only way to do it is this is the reason Kepler exists. You have to go to outer space where there's no atmosphere to blur the starlight. There's no sun coming up, because you don't know when that hour is going to be, right? You got to just stare with an unblinking eye for a year and wait for that little dip in the brightness. And that's, there must be something there. And one dip doesn't tell you much. Like, you're like, all right, that's interesting. You got to wait another year. You don't know what that year is. Is it 362 days? Is it 400 days?
Right, because you don't know exactly when
you got to wait.
Originally, is that what you're saying? You don't know when it dipped originally the first time, so
that's right. We launched Kepler in 2009, and you're just staring, and you're like, all right, I got to watch for 1 year minimum just to see two dips from an Earth around a sun. If you're looking for that same kind of system, but two dips is still like, well, maybe this is something, right? This could be a false positive. I only got two little dips, and so we said you had to have three dips. You have to have basically 2.5 solid years of like staring at something, basically 3 years, to know there's a planet. And that was the Kepler mission, like mission design. You got to stare at a buttload of stars with an unblinking eye for like 3 or 4 years.
And is it one part of the universe? Is it staring at? So it obviously can't take in the entire 360.
No, that's right.
It's got to just look at one part.
Yeah, the Kepler field of view. The Kepler field of view, it's like if you held your closed fist out at arm's length, and like the little area, it's a little smaller than that. So that seems like a pretty big thing. That's much bigger than the sun. Right. But like, how many fists would it take to cover, the entire night sky?
A lot. Yeah.
Right. Yeah. So it's like 100 square degrees is the Kepler field.
That's great.
and then like the whole night sky is something like 40,000 square degrees, right? So like you need a lot of Keplers to watch the whole sky.
How did they choose which one, which direction Kepler was going to look in the
Yeah,
first
that's a great question. So what you want to do is maximize the number of stars you can look at, right? Like this is expensive. Rockets are expensive. Spaceships are expensive. So you got to do it right. So you got to look in a dense field with as many stars as possible. And the Milky Way, which is our galaxy, is this big band in the sky. And you don't want to look straight into the Milky Way because it's so dense with stars. I mean, this is why it's called the Milky Way. It's so dense with stars, it just looks like a white band.
Right.
And even with a space telescope like Kepler, it looks it's just too crowded. Too many things in the field of view.
Sure.
You know, it's like taking a low-resolution photo of a crowd. You know, you wouldn't be able to like distinguish the faces.
Yeah.
But you want to look like as near as you can go and still distinguish the individual stars.
Right.
And
So not space between the actual stars, but also a section that has a lot of stars at the same time.
That's right. You need enough space, average space between the stars, so that you can see each one individually and they don't overlap too close for the resolution of your telescope. But you want it to be like full of stars, and that was basically the math. They were like, all right, how close can we go? And that's the math they did. I didn't do it. NASA. Smart people at NASA did it.
So you're telling me that it looks at one section of the universe. Now, is Kepler going around the Earth, or where is it going? What's it going around?
Right. So Kepler is physically located. We call it an Earth trailing orbit. Hey, what's up, Dave?
Is that your buddy?
That's my brother-in-law.
All right. What's going on?
Kepler is in what we call an Earth trailing orbit. So it's at the same circular distance from the sun as the Earth is, but it's going just a little slower and like in a slightly eccentric path. So it's slowly drifting away from us, but it's at the same distance. It's kind of moving along the same circular orbit we are. And so it's slowly drifting away. So at this point, it's like 94 million miles from us.
Oh, wow.
But it's like the same distance from the sun we are. This means it has a fun, cute property that like in about 50 or 60 years, it will go all the way backwards around and catch up to us in our orbit.
That's great.
And like, I mean, okay, like it's not going to get so close it's going to hit us. It will get a few times further than the moon is. But Kepler will come back around. And so my hope, this is not endorsed by NASA. This is like Jim Davenport cares about this.
You're hoping that data could still be reported once it cuts close again?
I'm hoping that in like 60 years, we have the technology and like the civilization that's like, that was such an important thing. That's like an amazing artifact. Let's go get it and put it in a museum. Right? Because right now, if Hubble Space Telescope died, the mission plan is to send Hubble to burn up in the atmosphere so that it doesn't land on somebody, which is a good thing. You don't want it to land on you. But Kepler is out there, like it's drifting away, but it'll come back.
I didn't know that. I thought it was, you know, I didn't know that's how it works. So yeah, it's pretty amazing. And if it didn't, if we couldn't retrieve it, is it still just going to keep going back around until some sort of space debris eventually runs into it, or?
Yeah, I mean, I think the models that I've seen suggest that it is stable up there for hundreds of years.
Oh, wow. That's crazy.
Maybe thousands of years. It kind of depends on if the moon kind of bumps it around in the orbit. Like the gravity of the moon could bump it, and that could cause it to go a little wacky. But like most likely, it's stable up there.
That's
how amazing would it be if we could like go stick it in the museum when we're old? Like our children could go see this thing, our grandchildren could go see this thing in the museum. I think it's such a cool mission.
That's amazing.
It'd be amazing to get.
So back to the data that you've been reviewing. You know, one of the questions that I'm just fascinated by is, you know, for you, what's a good day, month, or year at what you do? What's something that you could go home and be like, today that was more progress than what I did yesterday.
Right. That's an interesting question. A good day for me. I mean, being an astronomer is like most jobs where you sit at a desk and, you know, your daily task is not so well defined, and like, you know, you have like a little too much free time. And so a good day for me is when I'm excited and I'm focused. And that usually means that I'm writing. I'm either writing code or I'm like writing words. I'm like writing a paper or an article or like a blog post to communicate science or something like that. But, you know, a good day for me is either producing something like that, or my favorite days probably are like just going off on wild tangents. This is probably like academically the coolest thing about the job, is that like a super productive day is one where you're like, huh, that's weird. I have a curious idea. This might just be crazy, but let's just jump down this rabbit hole. And then it turns out to be something interesting or not. Like, again, science is a life full of failure. I have tons of ideas that turn out to be just like, well, that was very unintelligent, and I should have known better. But like,
I suppose you Google first before you even go down that rabbit hole.
sometimes I like fail to Google. That's right.
Yeah.
That's literally true.
I just saw a question from LBK. She wants to know, what are you coding? What language are you using? And how do you apply that? I guess my question is, how do you apply that to what you're doing? That's right. Yeah, that's a great question. So mostly I'm using Python. That has kind of become the major player in the astronomy community right now, is Python. I would say I was a late convert to it. I actually used a expensive proprietary language, which is still close to my heart because it's what I learned to program on, called IDL, which is mostly used by like atmospheric scientists, and so like most of the really ugly weather maps that you see, or like hurricane trackers, a lot of that's like IDL maps. So like a lot of geo people use it, but Python has become like the big language. There's a lot of people working in C, and there's a few people working in R. But you know, that for the most part is where we're at. There's a lot of old Fortran code still floating around that we deal with, but nobody wants to touch it. And through Python, you're seeing those waves and the lights that you're studying. That's studied through coding or something.
Yeah, that's right. That's right. Yeah. So when we teach, when we teach programming, we're not teaching it usually like you would in a computer science class, where you sit and study like the theory of algorithms and how to make code fast. We study a little of that. A lot of what we do is what we call data exploration and data analysis. And so, the two big things I'm doing is, how do I take data in whatever form it's in? If it's a picture, if it's a spectrum where light is broken up as a function of its wavelength or color, if it's some kind of time series thing, is it something more complicated? Is it a map? Is it, is it a messy text file that somebody just like quickly spit out in Excel? Like, it can be data, it can be a lot of things.
Right.
So number one, I got to figure out what data is and how to ingest it into the computer. And then number two is like, I got to make graphs. Like, for me, that's the biggest part of my workflow. Is I think almost personally entirely in graphs. And so when I'm talking to people, I have a notepad and I'm like sketching, like, okay. What you're telling me is that this line goes up instead of down. Okay, I can measure that. I'm thinking in the sense of like X versus Y.
Right.
I guess Y versus X.
That's really interesting. So I've obviously, been looking at what you've been doing, and first of all, your video blogs are great.
Thank you.
I definitely, I'm going to give a shout out to your YouTube, at the end where, I want everyone to see your video blogs. You recently
my camera right there.
That's
stage background camera.
It's great. And you recently went to the test launch, which, obviously that's kind of your next project. But, back to Kepler first, what are you still, now that the Kepler mission has ended and TESS has launched, which you got to see and close, which was super cool. What is it that you're still looking for? What is it that, how long can that continue before it's like, okay, I'm going to transition over to TESS?
Right.
How soon is that going to happen with a transition?
I mean, the honest answer is the Kepler data is going to keep being part of my workflow for like probably 10 more years.
Oh, wow.
But it's so special and so unique. TESS is going to do so much. Let me not undersell TESS. TESS is awesome. And the what's up, Jim Farkle? What's your question? But the truth is, TESS is not a perfect replacement for Kepler for all the science that you would want to do. It's different. It's a different kind of mission. And so there are aspects of, so for example, TESS has a larger field of view than Kepler, but it moves, it's pointing, it looks in these like chunks, and it moves every month. It doesn't stay fixed like Kepler did. The idea is, the idea is to like spread it out over the whole sky. Never socks with sandals, never once. That's the answer to that question.
I might be guilty of that times, though. I apologize.
It's actually a really common Northwesterner thing. So I can't say that I've never done it. I can just say it's never acceptable.
There's a difference.
That's right. That's right. So the reality is I would probably be working with both Kepler and TESS simultaneously. You know, like the real beauty is what are the questions that you can ask with Kepler that stared at one chunk for a long time versus TESS that stares at a wide chunk for a month. Right. You know, when you can learn to use both of them together magically and harmoniously, like then you're really working with it, because then you can like ask your questions both broadly and specifically, and I think that's where I want to go is, you know, what do I do with like little snapshots of each star, of like a ton of stars, 100 million stars, right, and then like really focused observations of a couple 100,000 stars.
Let's say you go in a year from now, you find something strange with Kepler's data that you didn't see before. Can you call up someone and say, you know what, can we point tests at that same, you know, part and go back there and study that further? Can someone with that like that, I guess, already do that?
The answer is sort of. Like, so TESS right now is like fixed in where it's going to look for the next 2 years.
Right.
So they've already like
There's
said,
no
they've already declared this is where we're looking for the next 2 years.
Right.
But they have a mission review after that, and there could be a review. Now, some telescopes don't have that like fixed like observing cadence. Sometimes, like Hubble Space Telescope, every year you can apply for observations. Actually, I think twice a year you can apply for observations, and so that's the kind of facility that we found something really cool. And this would people have, I mean, because I haven't been so lucky, but some people have found like, OMG, this is an amazing planet. We need a HST, a Hubble Space Telescope, or a Spitzer Space Telescope image of it right now. And you can sometimes get one in a couple days if the science is like mind-blowing enough.
Right.
The director of the telescope
reviews that and says, okay, that's worth.
Exactly. There's like a limited amount of time. They call it like director's discretionary time, where like the director, whoever's put in charge, says like, all right, this is too big a deal. We can't miss this. And so they will like interrupt whatever else is going on and be like, okay, we're going to give you that special image. You know, it's
NASA that approves it.
It's somewhat NASA, yeah. And I don't actually know who the director of HST is right now. I should.
No, but that was a question that I was going to ask for you: is how does what you do associate with NASA? Because you're technically a third party. You work at a university on you know, the research science team at the University of Washington, correct?
That's right. Yeah. So my relationship with NASA is totally as a citizen of the United States and planet Earth, and so most of what I do is using like publicly available data. And that, again, going back to like Kepler really showed us how to be open with our data and with our methods, both with other scientists and with the public. Like you can go to the NASA webpage that hosts Kepler, and there's a link to like the raw Kepler data. And anybody could go, you know, I don't know what you would do with it, but you could go and get it. And same with Hubble Space Telescope. All that data is publicly available.
Yeah, I just wouldn't know what to do with it if I got it.
But you know what? Like there are people, like there are like aerospace engineers and like computer programmers who actually use this data as like tests for algorithms they're developing or for systems they're building.
Right.
So it does serve like other purposes.
Sure.
My relationship with NASA is, yeah, both as just like a fan. Like I got my NASA mouse pad, you know, like go NASA. But
awesome.
I got
my NASA jacket. So
there you go. Yeah, right. See, there you go. But I also have a research grant from NASA that is going to fund me personally for a year of work.
Yeah, you've gotten grants over the years, and I was going to ask you about that. And how is that money applied to, you know, where does that go, and how do you use it?
Right. So, you know, going back to life as an astronomer is like full of like competition and failure. So much of what we do is like applying for funding because money is limited, tax dollars are limited, telescope time is limited. You know, we don't have infinite Hubble Space Telescopes. We have to compete with each other for like the best idea or the most exciting idea. And that's the same with money. And so we spend a lot of time. I'm in the middle, in fact, this week of writing a research grant to the National Science Foundation to do some work. It will include Kepler data, but other resources as well. And this is something you'll spend weeks doing every year, is writing these research grants. They end up with these like 50-page documents of all this extra bureaucracy you got to put in. That's part of the job that is not so glamorous, but is, it goes back to needing to communicate your science.
So this one that you're applying to now, if you got the grant, what would that be applied to?
Yeah, so that grant, most of that money would go towards paying a student to work with me and another faculty member at the University of Washington. So it would have about 3 years of funding for a student, a graduate student. It's like a living salary and their tuition and their benefits, and travel to a couple of scientific conferences. And then it would pay my salary for a couple of months and this other professor's summer salary for a couple of months. So, it's supporting us to work for about 3 years.
Cool.
And kind of build our group and build our momentum in this. And that's the same with this. So with NASA, I have a grant, and actually I have a grant with the test program as well to do some early science from tests. So, so this is part of the gig, is you're applying for money and and trying to find ideas that are exciting. Sorry, say again?
I said it's a shame how much time it could probably take up from taking away from the things you're supposed to be doing. That's what it sounds like, at least, when you're telling me all the 50 pages of just ridiculousness that you have to probably.
I mean, it's important because tax dollars are limited and they're important. And like, I think there are philosophical reasons. Okay, of course I think this because I'm a scientist, but there are philosophical reasons why we ought to fund science as a society, and why that. There's totally important room for private funding. Some of my money comes from private foundations. I think that's really important. But I think it's we gotta, as a society, we have to fund science, because
that was a question from one of our followers. I'll read you the question. It was from A. Showshine. He goes, "Why do you think continued public funding for NASA is important for the future?"
Yeah, I think there's there's a ton of answers, and NASA spends a lot of time answering, and scientists spend a lot of time answering this question. A couple things to me, these are off the cuff emotional answers for me. Okay, first and foremost, technology and human civilization and the advancement of it. We don't know where the next breakthrough is going to come. Pure research, pure science for science sake is going to invent things that matter someday. E.g., for example, this phone I'm talking on has components that are integral to the technology revolution that NASA has helped create. The camera in this phone, the internet that it is talking through, so much of this is in part played by pure science research, not just NASA, but some of it is NASA. And that goes for healthcare and all these things. NASA, on the whole, it's amazing to believe, but on the whole, NASA basically makes us money. That's a good incentive to pay for it. You develop technology. The other reason, and this is not the most complete reason, but emotionally for me, we are training most of the students that I work with, and this is true for all science and technology PhDs. Most of the students I work with don't become astronomers, right? There just aren't enough faculty and research staff jobs out there for us all to become astronomers. And most people don't want to spend 6 years in graduate school and, blah, 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 become a PhD. It's a lot of work, and you don't get paid that well. But every student that I've worked with, I would like to believe, has been left a little more tech savvy and able to do a little programming and data analysis and think about the world critically. And I think the dollars that NASA and the National Science Foundation have spent on me that I have then given to students and given as opportunities to students, I think that's money super duper well spent. Right. Because I spent a ton of time mentoring young academics and young critical thinkers to view the world and to interact with it. The beauty. Okay, I'm going to go on a tangent. The beauty of science, in general, the beauty of science is that it belongs to everybody, and that's what makes astronomy so great. Because to appreciate astronomy, all you really need is to go outside and look up, right? The seasons change, the moon moves around us, the sun comes up every now and then in Seattle. The science of astronomy is right there. You go outside, the night sky is dark. Why? Why is it dark? Why aren't there enough stars to light up the night? Behind that question that has made man curious since, I don't know, crawled out of the cave or whatever, the primordial soup or whatever. These basic questions about why is the night sky dark? Underneath this is mysteries of our universe, of the cosmos, that belong to everybody. And I think that's great. And along the way, we teach people to think critically about the world.
I think those are great answers, and especially, and it's true, the technology that I feel has come from building these rockets and sending people to space has then been applied to so many other, facets of life. And for me, my personal answer is, because the Elon Musk, wanted to get to Mars. It's basically making a duplicate hard drive of Earth on another planet. The fact that we're all here on this one, place where if anything can happen, and it's kind of like expanding humanity before it's too late. That to me is why I feel like the continued funding of NASA, or and all of their affiliate SpaceX, and is so crucial just to expand humanity and getting past here.
Human spaceflight is super critical to part of this, and a lot of like pure scientists are like, human spaceflight, just send telescopes, they're more interesting. But like I grew up like loving human spaceflight too, like a huge Apollo nerd and moon mission nerd. Like I went to space camp on my own dime after working at a burger shop for a summer as a 16-year-old. Like it was like, it's important and it resonates with the soul, and that's not to be ignored, right? The inspiration benefit is like humongous.
Yeah.
The good, keep spamming the like button. That's a good idea. But like, okay, there's one other like critical thinking part. I just said that science teaches us to be critical thinkers.
Yeah.
So let's turn this around. I am all about like mission to Mars, mission to the moon. I applied to the astronaut corps during the last call year ago. I was not selected, but I'll apply again.
Keep doing it.
But let us remember that until we make rockets cheap and like the USS Enterprise a reality, like we're stuck here. So like there's a whole bunch of science that it's important that we make sure we don't mess this Earth up.
Yep.
and life up here. Like I'm all about, and okay, like Elon Musk knows this and he's also working on stuff here too. But like, like it's important to remember, like we got to be driven by both what's out there and what's right here too.
Yeah. I went to Kennedy Space Center last April, and it was astronaut Bruce Melnick. I think he said he applied like 9 years in a row and finally got accepted. Yeah. So you're not the first.
Nope. I'll keep trying it.
Keep trying. So
you gotta apply.
Some more fun questions, I guess. Favorite science fiction or not science fiction, or science nonfiction book, movie, podcast.
Yeah. Okay. Book. My favorite, like the sci-fi book that got me excited about reading again. It's not the greatest book in the world, but it got me excited about reading again, was Moon is a Harsh Mistress by Heinlein. It's, like 1960s style sci-fi. Some aspects of Heinlein and that era sci-fi don't hold up super well, like in our progressive present, but it's a great bit of sci-fi. I really like that. That's my favorite book. I really liked The Martian, but I really liked The Martian on audiobook. The performance that like whatever you can get on Amazon, I got it on CD. That performance is like, I think it's better than the movie, and I think it's better than the book. So that audiobook kicked total butt. Go buy that. That was awesome.
I'm a huge Audible person, by the way. I have all my books I listen to on Audible.
Go listen to the Martian on Audible or whatever. Like it was top notch. I really enjoyed that. And then my favorite sci-fi movie. Oh, that's hard. I got a bunch of like DVDs, but I got to give the love to Apollo 13. Apollo 13. I went and saw Apollo 13 when I was like in the 4th grade or whatever, or 5th grade with my dad, and it was like, they said a few more bad words and whatever. It was a little more exciting than I was normally used to seeing it, but like it was one of those like, oh, this is amazing, as like a little kid, having my mind blown as a little kid. And Apollo 13 is still like, that's the movie. Like if I have the soundtrack,
that film, and the composer, it's just, everything about it. It's just it's uplifting. It's a great story. I was actually just watching something with Ron Howard where he was talking about it, and he was saying, when he was doing like the showing it in previews, I guess, and one of the feedback from one of the viewers was like, this movie sucks because there's no way this could have happened. It's not possible. Yeah. It's like. No,
it literally happened, dude.
It happened. And the person didn't know it was a true story.
Yeah. What I love about Apollo 13 too, as like a movie nerd, is they did the zero gravity shots for real. It's the only movie
with the plane, or they dropped it.
They did the Vomit Comet, right, where it does the parabolic flights, and you get like 30 seconds of zero G. They built Apollo command and landing module inside of the Vomit Comet, the KC-135 Vomit Comet, and they sit there and did this for days. So all the zero G shots in Apollo 13 are the real deal. Tom Hanks, OP Tom Hanks, right there.
So Tom did that too. He went up in that plane and he did that.
All the actors when they're that first scene where they like get into zero G and they're like opening their gloves and they're laughing is just like straight out of camera. Like they were just like having fun during that first take or whatever. It's amazing.
They must have gotten sick though too, right? I mean,
yeah, I mean they call it the vomit comet for a reason, man.
Right.
But like that to me, like you're never gonna beat that. No CG.
Yeah.
I mean, there's CG in the movie, but like all those zero G scenes, all that enthusiasm, like puffiness in their eyes as they're floating around, their hair like wafting, all those tiny things, gives it that quality that like when they're talking about going home, when they're talking about those, they're doing their job as actors.
Right.
You can really buy it because they are. You can get to the place.
That's amazing. Yeah. So every summer in New York City, the Intrepid Museum. Have you been to the Intrepid here?
I've been to the Intrepid. Yeah, it's really
Enterprise,
cool.
right? That's and so every summer, every week, I think on Tuesdays they'll have movie night at the Intrepid on the deck of the Intrepid
cool.
for the stars. 2 years ago I went. It was Apollo 13. They had the author of the book come and speak before the film. It was really, really cool.
That's
so if
awesome.
you're coming to New York during the summer, look up movie night on the Intrepid. So
that's cool.
Yeah, it's all the sci-fi and real science films, and Apollo 13. Yeah, that's a great one. And I guess lastly, podcasts. Is there a podcast you listen to or?
Okay, I will shamefully admit I'm not on the podcast wagon. I had an old car up until recently that had no ability to plug my phone in.
Yeah.
and I had a lot. My previous job, at my previous university, I had a long commute, and so I drove a ton. And so I didn't listen to podcasts last few years. So like I'm going to shamefully admit that I'm not on the podcast wagon.
It's all good. There's one podcast which I was late to the party on, The Habitat. Did you hear about the Habitat podcast?
I haven't. No.
So it's about high seas, which is the habitat that NASA built in Hawaii, where basically 6 astronauts are staying there and they have to act as if they are on Mars. All communication with anyone on, in the world has to be 20-minute delays in emails and calls. And whenever they go outside the habitat, they have to put spacesuits on. And they did this for an entire year in this tiny, tiny habitat. And so there was one journalist who had them have a voice recorder and was asking questions, mailing it to them, I guess, and they would record it and send it back. And it's really, it's fun. I think it's like 30-minute episodes. There's only like 7 or 8 of them, but you see, what happens. There was a relationship on board that wasn't,
cool, right.
So like it was good. It was juicy. It was fun, and it was very entertaining podcast. So look up the Habitat.
The Habitat. Check that out.
Yep. All right. So my last question, then I'm going to go to some questions that I've taken from some of the followers.
Great.
So I guess, my last question would just be, if there's one thing that you would love to find out about in this lifetime that you don't know about yet, what would it be and why?
I have to go big and say life. I mean, like that's, you go back to movies that were important to me when I was a kid, like Contact, like those big sci-fi movies. Man, if we found life out there,
Changes the game.
It would change everything. It would have the potential of being like a transformative moment in humanity.
Yeah.
And it wouldn't happen at first, right? Like most likely we're going to find life as like,
microbial. Yeah.
Bacteria, some fossil bacteria, even maybe like, it's not even alive life. It's like dead life.
Right.
Like Mars will have life or something, right? Like something like that. But the implication will be so powerful.
Yeah. So
broad that like, we're not alone.
Yeah.
And that's so powerful. So one of the things to that end, so right now I'm in my job, I have about 4 years of funding. I'm actively writing grants to get more funding. But right now I feel like this is about as stable as I'm going to be for a while. And as I said earlier, like you are always rolling the dice in science. You don't know if what you're doing is going to be hot. You don't know if other people are going to be excited about it, if you're going to get money to do it. So you got to just follow your guts. You got to follow your nose, as it were, and just go what you think is cool. And so one of the things I'm starting, amongst other projects, one of the projects I'm starting is a SETI project, so the search for extraterrestrial intelligence. And it's not like my primary thing. It's not what I'm spending most of my time on. But like I feel like if I don't do that, then what did I get this PhD for? What am I an astronomer for? Like if I'm not spending at least a little time thinking about the biggest possible question that I can answer, that excites me, that like, You know, as a little kid, I would look up, you know, in like rural Washington in the dark skies and be like, are there aliens out there? And, you know, like if I'm not doing that as an astronomer, what am I doing?
That makes sense. Did you see that article that's been viral the last 24 hours about those Harvard guys that think that cigar-shaped asteroid that passed us, I guess, what, a year ago?
Yeah.
Could have been, you know, not manned, but maybe debris or unmanned, you know, UFO looking for data.
Yeah. So I was visiting Penn State when that was all happening originally last year, a year ago. And Jason Wright, who's a major SETI researcher, and I were having dinner, and we were talking about this even before this article, you know, so a year before this article came out. We had the same conversation of like, not like, is it aliens, but like, what would it have to be aliens, right? You know, like, how would we convince ourselves that's an alien spaceship? And like, that's an interesting question, because like there's a lot, like comets are like crazy. They move around. They have these big plumes of material that come out that change their orbital direction. Like, if you didn't know what you were looking at, you'd think a comet was really strange and really suspicious. And so there's a lot of things like that. So Oumuamua was the name of this asteroid, this interstellar asteroid. And, you know, we have to ask the question. And that's one thing that Avi Loeb at Harvard and others are good at doing, is like, look, no, and to be fair, they're not saying we think this was an alien.
And we'll never know for sure, but
right. They're saying like, let it be, you know, let us just note. We can't rule that out. Right. Yeah, there's some weird things about it that we can't answer, and one of those explanations could be aliens.
Right.
But with extraordinary claims requires extraordinary support.
What about that star that had some weird dimming on it?
Oh yeah.
Again, can you dive into that really quick? I know.
Absolutely.
I appreciate your time on all this, and if you have to go at any point, you tell me. But this is fun. So
no, this is great. So that star, that is one of, I think, the best discoveries from Kepler. Actually, is called Tabby star, or more properly, Boyajian star. So the lead author of the discovery was Tabitha Boyajian. So it's been nicknamed after her. It has some telephone number associated with it. This is the actual ID number in the Kepler catalog that I don't ever remember, because it's like a 10 number. So Boyajian star is a seemingly normal, just boring F-type star. That means it's a little hotter than the sun. F is like, they've ordered it's not important. It's slightly hotter star than the sun, but it's like a normal looking star. And then, like one day, while Kepler was staring at it, it dropped in brightness by like 20%. Not in one day. It took a couple days. And then over a few days,
that drop is that like an insane?
You know, that we can imagine reasons. Like if there had been a companion star moving around and maybe blocking the light,
right?
That would be plausible, and we see those kinds of things all the time. But when that happens, there's kind of a regular shape to it. It makes sort of a uniform, like as it goes in front of the star, then comes away from it. You get sort of a uniform pattern, and then it usually repeats. And then follow-up data will show like, oh yeah, there's evidence that there's another star there or something, or there's like some gas or some dust or something there. And nothing made sense. This thing got super dim and then went back up and then was like normal again. And then randomly did it again to a different depth with a different profile. And it did it a few times with no warning and no discernible pattern whatsoever. And what I love about it is not just that it was like so weird. Like we can, as astronomers, we're trying to concoct scenarios that make sense. Like maybe it's some kind of comet. Maybe it's a dust thing. There's a big clump of like a dust cloud moving through, you know, like weather.
Not like everyone else saying it's aliens.
Well, the problem is, there's no good explanation, which the media will fill in as like, and therefore it could be aliens.
Right.
You know, and like, so there was a paper that was written right after the star was discovered, which was like, what if, again, same kind of thing as with this Oumuamua, the interstellar asteroid, like what if we imagined aliens were in the process of building like a Dyson sphere, like this big sphere to totally encircle a star to capture all the starlight. What if we were catching them in the construction phase? Like maybe what we're seeing, maybe these dipping events are actually structures moving in front of our line of sight that are like, you know, scaffolding or something. Or I don't know. I mean, I'm interpolating here a little bit. Yeah. But like, you know, this was kind of like the one of the hypotheses that was put out there. And of course, there's no other evidence of this. So how would we know? Who knows? What I love about Boyajian star is not just that it's a mystery, and it's still a mystery. I've written a paper about it. A bunch of my colleagues have written papers about it. We're trying to get anything else we can learn about the star to try to solve this mystery. And so far, we don't have a great solution, which is great. I love the mystery. What I love about it is it was discovered by amateurs, by like regular citizens of the world who are like on their own, like going through every single data file from Kepler and just looking for things by eye. No fancy tools, just like images on a website. And some people were like, "Ah, that's weird. I wonder what that is. Maybe that's some like binary star thing." And then they reached out to an astronomer, Tabitha Boyajian, and she was like, "Huh." And like that moment is what started that whole project. And that's amazing, right? Like it was just people, not astronomers. Well, I mean, citizen astronomers, you know, the world, people who found it. And I love that. I love that that data was sitting in a hard drive in NASA, publicly available. And like astronomers like me probably had looked at it and like, yeah, that's junk. I don't know what that is. Throw it out. Like nobody took the time to like notice it. And none of our fancy like algorithms or anything like said like, ooh, that's cool. Instead, it took a human being to be like, oh, what the heck is that? And then it stood out. And it's become this grand mystery. She gave a TED talk. She, you know, it's like it's been this whole thing now.
Amazing.
How many things like that are like just hiding in the mundane data that we have taken already?
So, in other words, our viewers should go start looking at the data now.
So totally, I will shamelessly say there are a bunch of what's called citizen science or like amateur science engagement projects. There's a great website called the Zooniverse, Z-O-O, Zooniverse. It's a portmanteau. You can Google it. Go to the Zooniverse and check out like in these projects. It's not just astronomy. There's like all kinds of disciplines. Like get involved in like some of the science because your eyeballs, your brain are really helpful pattern finding tools that will be used by scientists to like classify things, to find weird stuff, and it makes a difference. These projects are really exciting, and regular people can go for like 10 minutes and go help out, and it's actually really helpful.
So when can you look at the data of that star again? I mean, how frequently can you look at?
So Boyajian's star, at least from where we live, is up about 6 months of the year in the night sky. So it gets observed now basically every year by somebody. It's a little too faint to be studied in detail by TESS, but I guarantee somebody will try. TESS will scan over it, but it's a little too faint for TESS is a smaller camera, and so it doesn't have as much light gathering power. So it's a little too faint for TESS probably, but I hope in 6 months we're talking and I'm like, I was wrong. It's right there. We can see it. Mystery solved. That would be great.
Well, all that's amazing stuff. And all right, so let's go to some questions. So
please.
Well, one person had asked, you know, Alan DeSimpson had asked what happens to the parts of Kepler, but you explained it's going to keep going around and around, and you know, maybe one day the technology will be strong enough that we can retrieve it and
maybe they're not promising anything, but I hope.
Okay, so Reb_of2 asks, how long is TESS expected to last for in space?
Okay, so TESS is set up to run for 2 years. The first year it scans the southern sky, so basically the sky you can see from the southern hemisphere. In the second year, they flip the telescope over and they scan the northern sky. But they've got plenty of fuel and plenty of hardware to run for a lot longer. Right. So we have heard estimates that TESS could, if everything goes well, run like 20 years.
Oh, wow. Which
would be amazing. It wouldn't be 20 years of constantly staring, but for 20 years, you'd get like an annual pass over your favorite star. And even like a month of data every couple of years would be an amazing data set. Like how many cool things are going bump in the night to take 20 years to go around? You know?
And anything past 2 years is, I guess, considered a success as long as it did what it's supposed to do, and anything past that is a win, you know?
Yeah, like NASA always designs these missions with like a minimum lifespan that it needs to hit to be a success. And for Kepler, it was 3.5 years, and for TESS, it's like 2 years.
Yeah, and Kepler destroyed that by, what, 6 years almost? I mean,
That's right. So, you know, and like some of the rovers on Mars have like mission lives of like 90 days and have been going for like 15 years.
Oh my, that's crazy.
So the rover they're out of contact with right now, it ran for like 15 years of a 90-day mission. Like you're getting your money's worth.
Are they just aiming really low? No, like they must know it.
No,
you know?
Space is hard, man. Like we like to brag about these success stories, but like let's think about Mars. Half of the spacecraft we've sent to Mars have been destroyed.
Right.
Have not landed, blew up, missed. You know, like it's hard.
It's hard.
So you gotta over-engineer them.
Yep. I just saw a question from Robin Jill on this test. You know, will it still be relevant in 20 years if it stays that long with all the new technology?
Yeah, I think that's an insightful point. Like your iPhone from 3 years ago is, you know, kind of garbage. Like the camera is like not so good. But Hubble Space Telescope is like 25 years old,
and it still gets incredible things.
It's still doing the best work, mostly because we've never ponied up the dough to build another one.
Right.
So it will be the best, provided we don't, you know, pony up and build a better, you know, a super test. Okay. Now that being said, the one thing you can't buy is timescale, right? You can't buy, if it's still running 20 years from now, there's nothing else you could buy that would buy you that 20 years of coverage. Like that just takes time. And think about 20 years on the scale of the universe. Like 20 years doesn't even cover the orbit of, you know, like Pluto's orbit is like 400 years.
Wow. Yeah, it's nothing. Is TESS going as far out into the universe or to our solar system, excuse me, as Kepler has been and where it is now? Or
no, TESS is in this like totally wacky orbit that like is in some resonance with the moon. And so it stays pretty close to Earth. And it's what they call like quasi-stable. So the orbit is stable for like 200 years. Right. That's the ultimate like lifetime test. Like after about 200 years, the moon's probably going to like shove it out of the way.
Right. You wonder if there's like an emergency where they need to repair it, if they could, because it's not too far away. But you don't think so?
Not with current technology.
Yeah.
It's moving in too wacky of a direction to catch.
Understood. All right, let's keep going down here.
Yeah.
All right. Okay, Arlecari, this is an interesting one. Has Kepler discovered any Earth-like planet orbiting a double star or even a triple star system?
I think so. I will admit, so Kepler's discovered something like 3,000 planets, and I don't know them all at this point.
Yeah.
We've definitely discovered Earth-like planets around stars, like Earth-sized planets around stars. And some of them are pretty close to like that sweet Earth-Sun size system. Like it's really hard like Earth is like pretty small rock by comparison. It's a lot smaller than Jupiter, so it's hard to find. But we found a bunch of planets around double stars, but they're not Earth-like. They're either like super Earth in terms of size, so they're like bigger versions of Earth, but they're usually further out. So you'll see like two stars orbiting each other, and then you'll see this planet like wandering around outside. We would call this a circumbinary planet. So there's a binary star, there's a planet wandering around the binary star. And that's something that Kepler has discovered several of.
Right.
It wasn't like, I mean, this is like the Tatooine kind of thing from Star Wars, right? Like imagine being on a planet with two suns.
Yep.
The problem is like, you can't put that planet so close that you're in that Goldilocks zone of like, ooh, it's nice and warm. Yeah. Or else the stars will like gravitationally knock the planet out. Right. So the answer is probably we won't find a lot of planets in that sweet Earth-like habitable Goldilocks zone around double stars.
Got it. Well, I appreciate that.
We have found some wide orbits.
So Instagram is telling me we have 1 minute and 20 seconds. I guess they limited us to 1 hour.
Oh, man. Okay.
So before I let you go, this has been amazing. And I know there's so many more questions we could have gone through, but I just want to give a shout out. Obviously, anyone can follow you on Instagram here, JRA Davenport. Twitter, same thing, JRA Davenport. And Mike, that's how you say it, right? JRA.
Yep.
Obviously, we're talking to James Davenport. You've been amazing. Thank you so much. And YouTube, everyone has to go check out your video logs. YouTube.com/James-Davenport. And I'm actually going to Virginia next week. I'm going to be seeing a rocket launch. They invited myself, SpaceFactsWax, and my brother, who's a musician, and we're going to go see the Antares rocket launch the Cygnus spacecraft, which is going to be carrying a lot of, I guess, experiments and food to the ISS. So
awesome.
Thank you so much. And is there anything you want to leave us with 25 seconds left to go?
25 seconds left. Science is something for everybody. It belongs to everybody. So go look up and look down and be curious, because you can understand the world around you. That's what science is. Yeah.
Love it. Well, thank you so much for this. It was amazing. And apologies to anyone we couldn't get to your questions. This Instagram limit